the advanced things.
Yeah.
Supposed to be negative side.
Okay. Oh, you're so lucky I turned that camera on because I would have flipped you off. All right. So, say it again.
You can't flip off your UK viewers.
Yeah. All right. That's for you, UK. Anyway, so I think I was sufficiently out of frame when I did that because I know where that goes. It doesn't matter. All right. So before we get started, Martin asked the question: are we finally going to get to do calculations next week? And the truth is. Oh yeah, by the way, I'm going to hand these out. These are stapled together. If you have several things that you have not gotten back, they're in here. It's not very many, but this includes the redos from quiz 2, which I finally got around to grading. So I'll just start these at the front and they can go to the back. So they're in clumps, and if you have anything that you know is outstanding, it should be in that stack. And that should give you back all of the work that has been graded so far. Now, the orals are done, and the results of the oral exams were somewhat mixed, and I find it partly as just kind of a reflection of the course. I know, or I've realized that there's just a real tremendous amount of material to be covered in this course, and we still have a lot to talk about, and there's actually sadly a lot of things we won't be able to talk about. Moreover, it's not just that there's a lot of different topics, but some of them are quite deep, right? I mean, you have to learn some math, you have to learn about these Lie algebras and Lie groups, and you have to learn about spinors, and there's no way in God's green earth that spinors are intuitive or easy. They're probably one of the hardest things in physics. And so I think I'm coming to terms with the fact that I might have put more on you than you could have taken reasonably in the time leading up till now. So I might try to slow things down a bit, and it's going to be at the expense of covering more topics. But the truth is just there's no point in trying to cover everything if you're not getting it. Okay. Now the good news is that somewhat similar to GR, for those of you who took that, the course changed significantly about halfway through. We did a lot of formalism, and then all of a sudden we were doing calculations, and the calculations part, you could follow that even if you weren't completely confident in all the formalism. So when we start doing calculations with Feynman diagrams and so forth, it's not necessarily going to require that you know every single in and out of how to do a Lorentz transformation on a spinor, for example. Okay, so I don't want any of you to feel like you can't proceed or you should give up on this course just because you might not feel completely comfortable with what we've done so far. Things, the flavor of things are going to change a bit as we proceed. So with that in mind, I have some topics that I'm going to talk about today, but I'm going to start by wrapping up a couple of details from the last couple of lectures on the Higgs mechanism. And then I'm actually just going to open the floor to questions if there's something that you would like to hear me talk a little bit more about before we get into today's lecture. So there were 3 things I was going to say about stuff. Man, there were 3. It's 1, 2, 3. 3 is good because 3 is the biggest. Okay, well I can't remember what the third one is, but I'll tell you about the 2 that I remember. So we had talked a lot about the idea that in the Higgs mechanism, a very important part of that story is taking the fields in our Lagrangian and looking at the fluctuations in those fields, and then asking how do the fluctuations change if the background field changes. And I kept giving you this sort of analogy to, if you take a lake and you drop a pebble on it, you get a little wave. And then I said, if we, change, but I didn't really complete the analogy. So I think actually I thought about this. I'm going to dare to go further with this analogy, but bear in mind it's an analogy. It breaks down at some point. It's not like quantum fields are not lakes. There's a difference, okay? But I think this is actually a nice way to think about it. If you have a lake and you drop a rock in it, right, you get this nice spherically expanding or circularly expanding ripple on the surface. And you can think of this as like a fluctuation, okay? And then you have the lake that the fluctuation is a fluctuation about, okay? But now you could consider, instead of a lake, instead of a lake, you can actually consider that your body of water is actually a waterfall. Okay? This actually changes the behavior of fluctuations quite a bit. For example, if I drop a rock in, I'll get so now this is from the side, but if I view it from above, I'll get these ripples, but those ripples will travel, and eventually they will do something quite different here, okay? So in all of this, it's fluctuations of the surface of the water. But depending on the overall configuration of the water that you start with, those fluctuations are going to behave very differently. Here, they'll just kind of sit still and they'll just expand outwards. Here, they'll move, expanding, and then they're going to do something crazy when they drop out of the waterfall. Okay? So the background field configuration that you start with, especially when it's non-trivial, it can radically change the behavior of the fluctuations. Now, the key though is we didn't start by saying I want to take the electron to be non-trivial. I took the Higgs field to be non-trivial. And then somehow the non-triviality of the Higgs field induced a non-triviality in the fluctuations of the electron. For example, it gives the electron mass. And you might say, well, how does that work? Well, you can think about it this way. Instead of saying, I'm going to do something to the lake, we can think of the Higgs field as the ground underneath the lake. If the ground underneath the lake is just flat and smooth and forms like a bowl, you're going to have still water in the lake, and then you'll get fluctuations that look like this. But if the ground is actually interesting, if there's some kind of drop-off in the ground, and you've got some channel and you're connecting two big bodies of water so this is flowing, then that induces the water to do this, and then the ripples in the water will behave accordingly. Okay? So the shape of the water is coupled to the shape of the ground. And in fact, if you think about it, we don't really control the shape of the water. You control the shape of the ground, and then the water just follows suit. So it's somewhat like the Higgs mechanism in the sense that the Higgs field, if it's trivial, things look one way, but if the Higgs field becomes non-trivial, everything that couples to it, its behavior changes. In particular, the behavior of the fluctuations change. Of course, we saw that functionally. We looked at the Lagrangian and we re-expanded it, and we looked at the mass terms that were generated for the fluctuations. But then we also saw it by looking at the Higgs potential. Okay, so this idea of Higgsing and spontaneously breaking symmetry. Oh, I just remember what the third thing was. I'm so happy. That's an idea that we cover in this class, but it is actually a very powerful idea that actually contaminates other areas of physics. So I feel like it's one that's worth you kind of stewing on, right? This idea of breaking symmetries and changing the behavior of things as a consequence of that. So one more thing. So one of the other things that I remembered is with regards to breaking symmetry, I gave you this example of the ferromagnet. At high temperatures, all the spins are random, and so it's rotationally invariant. And then as it cools, eventually the dipoles align, and you get some net magnetization. And then the invariance is rotations perpendicular to that. That's one example of sort of this temperature-dependent change in the symmetry. And that kind of parallels what happened in the early universe. Early in the universe, when it was small, it was hot. Everything was symmetric, and then as the universe expanded, it cooled, and eventually the symmetry broke, much like the ferromagnet. However, the idea of spontaneous symmetry breaking is everywhere. And it actually was one of those things which, when I was your age and I was taking physics and I started hearing about the idea of symmetry, this, that, and the other, no one actually explained it to me, and it bothered me. And so I would like to take the opportunity to explain it to you. We're in this room, right? And we're governed by some physics, and we can write down the Lagrangian that describes that physics. And one of the key things that we keep coming back to in physics is that it's rotationally invariant. Okay, things are the underlying physics of things is rotationally and in fact Lorentz invariant. right? But if I stand in this room and I look at that direction, and then I turn and I look at that direction, it ain't rotationally invariant, okay? That's Claudia, that's Zach. They're not the same thing. So how is it that the underlying physics is rotationally invariant, yet our experience of everything is not rotationally invariant? The underlying physics is translationally invariant, yet our experience of things is not translationally invariant. I mean, if I start translating up, things change. Eventually I leave the planet and I'm cool. But so where does this come from? All of this comes from spontaneous symmetry breaking. The truth is the underlying physics is symmetric, but we do not have access to the full underlying physics. We live in a particular situation, a vacuum, a solution to the equations of motion, and everything is just fluctuations about that. And the truth is that the solution that we're sitting in has the symmetry just all broken to hell. Okay, there's no rotational invariance. Now, don't get me wrong, you can approximately get rotational invariance, and you can approximately get full Lorentz invariance and everything, as long as you zoom into regions where you can ignore, like, you know, that Claire is there, and Zach is there, and David's there, and so forth and so on. Okay, so when we actually do high energy experiments, we collide particles going towards each other. That's not rotationally invariant. There's a preferred axis. We send things along a line, okay? Right? But, and for that matter, there's this big detector waiting out there to detect things, and it's not rotationally invariant, okay? But when you actually study what comes out of that collision, all right, if you send in these two beams with a total center of mass momentum of 0, so you send in beams of equal energy and they collide, then for all intents and purposes, when you study what can come out of that, you should expect it to be rotationally invariant. Because you're sending in 0 momentum. 0 momentum means there's no preferred direction, and so what comes out should be completely rotationally invariant. You should have roughly the same probability of seeing things in all different directions. So these ideas of these invariances, they're in the underlying physics, and they even manifest themselves in certain experiences, but they're certainly not our everyday, enjoyment of the natural world. All right, one more point, and this is going to seem like a technicality, but it's going to clarify what I expect from you in your 4th homework problem. So in the very nasty expression that we had written for the Higgs mechanism, yeah, there it is. And this is something that I was going to defer explaining to you, because a lot of the way that we explain things in this class is we draw Feynman diagrams, but I haven't taught you what Feynman diagrams are yet, so it's kind of putting the cart before the horse. But this is a subtle point, but I think it makes an idea that I conveyed in the second Higgs lecture about the gauge boson eating the Goldstone boson. I think it actually makes it calculationally clear. It's just I got to draw a Feynman diagram to show you what I mean. So if you recall, in the Higgs story, we got this big Lagrangian, and that big Lagrangian was written in terms of fluctuations of these things. So this was the non-trivial vacuum plus the fluctuation eta. This was 0 plus the fluctuation beta, and then this was 0 plus the fluctuation, which I just called A mu. And then the final Higgs Lagrangian was written in terms of eta, beta, and A. Okay? And what we found was that eta had a mass, beta was massless, and the gauge field got a mass. But then I said, oh, but this beta gets eaten by A. Okay, it becomes the 3rd degree of freedom that A needs when A becomes massive. So initially this started out massless, so it only had 2 polarizations, because massless states only have 2 polarizations if they're a vector. But when I give it mass, it suddenly needs to get 3, because a massive vector has 3 states of polarization, and it gets that 3rd polarization by eating beta. But I can show you where that actually appears in the Lagrangian. So I wrote a lot of nasty stuff, but at the very end, there was a term that looked like the following. This term is actually unique among all of the terms that I wrote down in that full nasty Lagrangian. And you're going to be looking for a similar term in problem 4 of the homework. Now, we know how to identify kinetic terms. They're the ones with the derivatives. We know how to identify mass terms. They're quadratic in a field with itself, and then there's some coefficient here. And we know how to identify interactions. Now what's interesting is if you look at all of the terms in the interaction piece of this thing, and you can go back to your notes if you actually wrote that thing down, what you'll notice is that all of those interaction terms involve 3 fields. They don't necessarily have to be 3 different fields. It could be an A with 2 etas. But there was always 3 things. This is unique because it only has 2 fields. And they're different. So it's not a mass term because you have to have the same field to be a mass term. So we can ask ourselves what this term represents. And that's where this gets interesting. And unfortunately, I have to kind of jump ahead to this notation of Feynman diagrams, but eventually you'll be experts in this. So let us suppose that we had a term which was cubic, so maybe a beta squared a mu with some coefficient. What this is going to do eventually for us, and I guess this is a preview of what's going to come, is this is going to provide a building block of a Feynman diagram. And a Feynman diagram is just it's a picture you draw of a process or a way of doing a process that is an aid in eventually doing a calculation. You're actually calculating a number. But you start by drawing the picture. It helps you organize the bits of the calculation. And what this kind of term is going to represent is a vertex. A vertex is where lines join. And that's where interactions happen. And in particular, that vertex would have a beta line, and an a mu line. Okay? So a product of 3 fields represents an interaction, which in Feynman, in the language of Feynman diagrams, is a vertex. It's where this thing is interacting with this thing via the emission or absorption of an A. Okay? And you can imagine there are also 4-point vertices, and that's actually about as complicated as we end up seeing in the standard model. But then that begs the question, what is this? Because if it was a vertex, it would say that a beta comes in and an A comes out. It's not, so jumping ahead, we're going to learn a lot more about how to interpret decays and so forth, but a decay is actually represented by something like that. It's an interaction. Okay? So this is something different. This is somehow a beta particle spontaneously becoming an A particle, but of course there's nothing that keeps this from coming back to a beta. So this diagram is actually something that we normally forbid in Feynman interactions, because what it says is there's no physical way to distinguish these 2 things. If something can just flip-flop back and forth, there's no way to say what it is. In fact, the way that we interpret it is exactly what I said in that lecture. We interpret this as just part of this. It's one of the degrees of freedom of A. Okay? So this idea that A eats the Goldstone boson, so beta was what we call the Goldstone boson. It's the fluctuation in that potential that's actually around the valley. The fact that the gauge field eats the Goldstone boson is represented by this kind of diagram. It's just that you don't differentiate beta from eta, or beta from A. It's part of it. And that's reflected in this term. So these terms, a quadratic in 2 different fields, they're problematic until you give them the right interpretation. And that is, I should not be distinguishing those 2 things as separate entities. I should not think of beta and A as separate things. You're going to be looking for something similar in the 4th problem of your homework. It's going to play a different role because you're going to be looking at fluctuations and the Higgs field that are coupled in this way. Okay, but I just wanted to give you an idea of what you were looking for in that last problem, in addition to all the nightmare of multiplying that thing out. Okay. And fortunately, this also gives you an idea of whether or not you did all your tedious work right, because you should see one quadratic term of this form pop out. But that'll be a quadratic term in eta and beta. Okay. All right, so now before we get into what we're going to get into today, are there questions? Yes, questions?
So we're saying that beta is a degree of freedom of our photon field?
Yeah, so it becomes a part of the photon field.
Okay, so that's analogous to what you're asking for us in number 2 by showing that the Z and the photon field are linear combinations of beta and W photons?
Sorry, in which problem? In 4?
Second problem where we show that they're
Oh yeah, no. That's a separate question. That's a separate question. That is literally.
Because that had the Weinberg mixing.
Yeah. That question actually. So remember that the photon and the weak boson are written as these linear combinations of the. Oh God, I'm never going to get this right. The I can't remember what we called these things. Do you remember from the notes? W3? B and W3. Which one was here, the B or the W3?
The B.
The B? Okay, so B.
It's plus.
Okay, I'm literally asking you if W3 and B are orthogonal. Based on that set of relations, can you argue that Z and gamma are orthogonal? And if you think about that for a minute, you'll realize what that means.
Okay.
Okay? And if you're confused, there's quite a few people in the room with grins on their face. Find them and ask them. It's a no. So it's literally just asking you to recognize what that linear combination is doing. Good.
For the Higgs field, we've talked about many solutions that are V1, V2, and U2. Is there like we can set different, we have different.
So
factors?
generally, the set of solutions, given the potential that we were looking at, were just subject to this constraint. And we looked at, this particular case.
And then we're doing another one.
In the homework, you're doing another
Is
one.
there a preferred one that maybe is there?
There can't be, right? There's all of these solutions are related by a symmetry. None of them are preferred. In fact, you can redefine this field phi 1 using that gauge transformation to turn one solution into another.
So there's not because do we get different physics out by doing different solutions, which we've seen?
So that's the point of what you're doing in problem 4 is you're looking at a situation where both of these are non-trivial.
So that's saying something.
And it looks, when you write down the Lagrangian, ostensibly like the physics of these two are different than in the original. So in the case we did in class, remember, if this was the only one that was non-trivial, this had a mass and this was massless. When you do this in the homework, you're going to pick a different solution. You're going to pick this one. And when you plug this in, both of these are going to be massive. So the naive expectation is the physics is different. But the point of the problem is for you to, by looking at this term and realizing that you shouldn't be distinguishing eta and beta, realizing, oh, actually the physics is the same, it just looks a little different in the way that it's written. So to give you a pictorial idea of why it looks different and what you should do to fix it, remember the sombrero potential. Phi 2 and phi 1. Okay, we studied this solution there. Okay, and what we said was fluctuations along phi 1, so right along that axis, are actually going up and down the sides of the valley. Whereas if I just move it along phi 2, so phi 2 is this way, at this point, that's important. Phi 2, this direction, is tangent to the valley. but tangent to the valley, it's flat. And that's why the mass of the beta fluctuation in the phi 2 direction was 0. Now in your homework, you're studying this point. If you take this point and you think about a fluctuation in this direction and a fluctuation in that direction, which is what eta and beta are, they're both going up the sides of the valley a little bit, but not completely. So if you start with these two fluctuations, it's clear that there is some linear combination of those, which is massless, and another one which corresponds to moving perpendicular to the center of the sombrero. Okay? It's just you've chosen to work in the language of phi 1 and phi 2, and so the two fluctuations you're working with look like they have mass. That you just need to pick a different linear combination. So in physics parlance, what we would say is, you're not working with the physical fields. The physical fields are actually the linear combination where one is along the valley and one is perpendicular to that. You just happen to accidentally choose to work with a linear combination of those physical fields, which is exhibiting this weird behavior of both of them having mass.
So would it be safe to say something like, we live with the Higgs field that is the bottom part of the sombrero at the physics is defined by that, but we can choose one mathematical construct from the solution we want to use? Because I mean, it wouldn't work if we chose one point and the other point, they contradicted like what it told us about the Higgs field. So each point along that.
So all of these solutions have to give you the identical physics at the bottom of at the end of the story. They have to give you identical physics. It's not obvious that they do, and that's what I'm trying to get you to see in problem 4. It can look quite different initially if you're here versus here, but truthfully, and it's through identifying certain things like this, they actually are the same thing. And the reason I can tell you the physics has to be identical is because this direction around this valley is a gauge symmetry of our Lagrangian. It can't affect the physics. The Lagrangian's invariant. Even after you've broken the symmetry, by moving from here down here, you still have a symmetry of moving around the valley. Moving this way is not a symmetry, but around the valley is still a symmetry. Okay, yes?
Why wouldn't we just use, so that we don't have to worry about that, some kind of cylindrical coordinate system? Because then our r-hat direction would always be the massive direction, and the phi-hat direction would always be the massless direction. Or theta-hat, or whichever. Because then our bounds would just be r squared is equal to mu squared.
Yeah, that's actually,
Can you break up a complex number into cylindrical
Write
coordinates
it
like
in-
that?
yeah, you can break up a complex number like that, but there might be,
Might change the derivatives, but
yeah, I mean, you have to understand, so the first thing is when you say complex coordinate, or when you say cylindrical coordinates, we're not actually talking about cylindrical space-time coordinates, right? I'm not going from x, y, z to r, theta, phi. This is field space. Okay, so you're starting to talk about, okay, I'm pretty sure I know the answer to why we would not do that. What is the chief disadvantage to cylindrical coordinate systems compared to rectangular? No matter what it is you're coordinatizing, whether it's space or field space or whatever, what's the chief disadvantage? It certainly makes certain calculations look nice, but what changes?
it only works if it's centered around the origin.
Well, yes, it only works if you're centered around the origin, but
The directions of the coordinates depend on each other.
yeah. So I'm hearing lots of whispers, but basically, if you write down a set of unit basis vectors, they're not constant everywhere. They change. And that actually, I mean, those who study general relativity know that's a royal pain in the ass, because the form of the derivative looks much more complicated than it would if you always choose rectangular decomposition of field space or space-time or whatever. So that the idea of varying the Lagrangian with respect to the field would become nightmarish if you used cylindrical field
Some
coordinates.
linear.
Yeah. But you could do it. I just don't know anybody that does.
If you had some linear combination of eta and beta in that term, it looks like you'd have.
In this one?
It looks like you'd have 4 degrees of freedom in that.
If you had a linear
If
combination
you
of,
had both eta and beta in that term. you'd have 4 degrees of freedom instead
in
of-
this one here?
Yeah.
No, you're gonna get something that's like this.
Okay, and then another one that's. Oh. Okay.
This is the term that I'm asking you to look for. A linear combination of eta and beta. You're still going to get something that's coupled to the gauge field. This part of the story is still going to play out, but I'm actually, in problem 4, I'm getting you to look for this term, because this term is the one that says we should not be distinguishing eta and beta as physically different fluctuations, because an eta fluctuation can turn into a beta fluctuation.
So you're saying beta and A are indistinguishable, but A has mass, beta doesn't. A is a vector, and beta is a scalar.
So, yeah, the interpretation of things, like what you're saying, is, it's actually very much like this story right here. And that is, you're sitting there saying, well, how can beta be part of A if A has mass and beta doesn't? Well, I might ask you, if you do problem 4 and you get that eta and beta have mass, how can that possibly be equivalent to a scenario where only one of them has mass and the other doesn't? And the answer is, it appears one way if you're working with a set of degrees of freedom, and if you choose a different linear combination, things appear differently. Things that were massive can become massless and vice versa. So when we wrote this down, and we actually wrote a beta and an A separately, we weren't using a good basis. We weren't using the physical basis. We should have actually just dropped beta, which I said we did, eventually with a gauge transformation, and worked with a completely massive 3-polarization state A.
Okay, I'm still kind of confused with it.
Okay, well, for now, why don't we defer this until after you guys have worked through the 4th homework problem and you've actually got some of this tedium under your belt, and then we can maybe come back and talk about it some more. Okay, other questions? Other questions? Yes.
So it's not. So when we came up with the Higgs, we just wrote the Lagrangian on the board.
For the Higgs
The
field?
Higgs- Yeah.
Yeah.
And then we said we were going to sort of talk about why it is the way it is later. But I'm still confused on sort of how we got that. So like for like the Proca, Dirac, and like Klein-Gordon, we started with something that I could sort of understand how we put these things together.
Mhm.
But I feel like we just pulled the Higgs Lagrangian just straight out of nowhere. Yeah.
Yeah, we did. So this is, and sadly, it is the one, like, to me, very disappointing part of the standard model. It's beautiful in the sense that it wonderfully resolves these issues of where did the electroweak symmetry go? How did the gauge bosons, the weak interactions, get mass? How do all the fundamental particles get mass? And they get it through this Higgs mechanism of coupling to this weird field. The disadvantage is it is the one place in the standard model where we have to put in an interaction that does not come from gauge symmetry. And that interaction I'm talking about is the Higgs potential. So the Higgs Lagrangian that we wrote down was just the Klein-Gordon Lagrangian.
Yep.
Right? But this was totally unmotivated. I don't even remember the form of it. Plus lambda squared over 4 or something. This was totally unmotivated.
Okay.
Okay, it's motivated only by the fact that we already know from having worked this out where it eventually gets us. But I can't say that this comes from some principle of local gauge invariance. It's just not the case.
So we basically just found something that works and said, it works, we're gonna we're gonna stick with all that.
Yeah, and so the truth is there's many things that would work. I mean, we talked about, some examples, like that it doesn't have to be this potential, like this could be like a wavy thing, and you can still break the symmetry by moving to one of those valleys, and that would just correspond to this being a more complicated potential.
Yeah.
What this is the simplest potential that you can do it with.
Mhm. Okay.
You can't do it with an easier one than this, so that's what we kind of teach. But the truth is no one is going to sit there and tell you that this is the correct Higgs potential, because we don't yet know enough about the Higgs. We've barely seen it, much less seen it enough to know its detailed form.
Okay.
So when we teach this, I shouldn't say this is the Higgs potential. All I can say is this is a possible form of the Higgs potential. It might be more complicated. Now, when I write down the electromagnetic interaction, getting it from a principle of local gauge invariance based on U1, that's the right interaction.
Yeah.
Like, we have tested the crap out of that, and we know it gives us the right answer. Same for SU3 and the weak interactions.
Third.
Yeah, Ron?
Is it always going to be tachyonic though?
Yeah, because the whole symmetry breaking thing kind of requires you to, at some point, be at an unstable point. And that's what the tachyonic part is telling us, is that you're sitting at a maximum. And then that explains how you would have changed, and that's where the symmetry breaking happens, how you would have actually rolled down to a different vacuum. I mean, if you started with a Higgs potential that looks like this, and you started here, you wouldn't ever go there, right? I mean, yeah, maybe through some semi-classical quantum tunneling, that's a whole different ballgame. But it's much more reasonable to say you start off at a maximum and then you've definitely dropped off of that due to some fluctuations. And of course, we talked about how you get to that maximum by the evolution of the potential over energy scales. Other questions? Yeah.
So if all these fields are coupled to the Higgs, how exactly did we find just a boson then with the Higgs? Is it?
How did we find a what?
If it's coupled, if we found fluctuation in just the Higgs to find the boson, or did it have caused some sort of coupling with the other fields, or how did that?
Well, all the other fields coupling to the Higgs is reflected in them having mass, right?
Exactly.
That's their. That is the reflection of their interaction with the Higgs field. Now, you can have a particle. You can have an interaction without claiming that you have actually created, per se, the particle in question. So what I mean is the following: when you have, oh Lord, I haven't drawn actual standard model Feynman diagram processes in a long time, so I'll probably never be able to pull this out of my posterior. But if I have a neutron, which is an up, down, down quark, then what happens is this guy decays via a weak interaction, and
Neutron to a proton?
Say again?
This is a neutron to a proton?
Yeah, so this is a proton, and then this is carrying away negative charge, and then the W can give you an electron and an anti-electron neutrino. Okay, you're going to sort of learn how to piece these things together in the next couple of weeks. So right now, I just want to use this as an example. And this happens. If you have a free neutron, it will decay. And you might say to yourself, oh, we created this. Well, you didn't really create it. It was a completely virtual state. All right, it didn't live long. And this is not the only thing that you would draw. That's different than saying I'm going to collide things together with sufficient energy that I create an actual W minus that exists and then eventually decays into other stuff. So you can have particles that are contributing to interactions. The Higgs is contributing to interactions because things have mass. But that's not to say that you created the Higgs boson. To create a Higgs boson is actually to manage something like this. Okay, and right now I know, like, you could have a gazillion questions for you. What do these diagrams mean, and what is real and virtual and all that stuff? And that's what we're going to be spending the next month talking about.
Is it possible to talk any more about what a bound state is like? That means
A bound state?
A bound state, like a neutron, even in a hand wavy sort of way.
Yeah, a bound state is when things are bound. So, no, so that's actually a really interesting question. And the problem with bound states, and this is actually kind of getting ahead, but since you asked the question, Henry, I'll try and answer it. Bound states are one aspect of physics which are beyond the calculational tools that we're going to develop. Because everything that we're going to develop is predicated on the idea that what you start with coming in and what goes out are free. And they only interact in a small region over a short period of time. Okay? Now, we're going to do things like this where we say we've got a neutron, which we all know is a bound state of a bunch of quarks. All right? And you're going to be like, didn't you just say you can't do bound states? And the important thing here is that I have a bound state and I end up with a bound state. And what's even weirder is within this bound state, these are actually acting as if they're free. They're bound, but they're free. The strong interaction is weird, and one of the points of what we're going to study is to learn why this is the case. But with the electromagnetic interaction, if I take two charged particles and I bring them very close together, they interact more and more strongly, right? Q over r squared, as r goes to 0, that blows up. If you pull them apart, they interact more and more weakly. The strong interactions are actually backwards. The closer you bring two quarks, the weaker they interact with each other. The further you pull them away, the stronger they interact with each other. So when you have quarks that are sitting right next to each other, say bound up in a proton, they're basically not interacting with each other. But we still call it a bound state. Because overall you can't pull them apart, because to pull them apart requires more and more energy. So this is a very fascinating part of the strong interactions. It's called confinement, and alternatively asymptotic freedom. It's asymptotically free because as you get them closer and closer at high enough energy, they don't interact at all, yet you cannot pull them apart. They're somehow confined. And proving those features is actually a very important, outstanding question in the standard model. And the reason it's outstanding is because you can't use the kind of calculational techniques we're going to develop, which is basically perturbation theory. These processes are manifestly non-perturbative. They can't be analyzed with these Feynman diagram techniques. So that's a story which will make a lot more sense after months worth of talking about these things. That's a good question. And just one second. And for that matter, we can't talk about hydrogen, right? I mean, hydrogen's a bound state of electron and a proton, and we can't describe it with these calculations. We know it exists, and we can describe it with non-relativistic quantum mechanics. We can even do relativistic quantum mechanics, but these calculations, these perturbative calculations we're going to embark on are just incapable of describing bound states. Yes?
So this might be you might not be able to explain it properly, but so if the strong force holds the quarks together and then also holds together like nuclei, how is that? Is it just the exact same?
What do you mean it holds together nuclei?
So like if you move like an electron or proton and neutron close together.
Sure. Okay, yeah, that's a really good question, and there's actually a really beautiful explanation for that, and I think Peter is the only one lucky enough to have actually seen this diagram. And that is, we tend to think of the force between nucleons, like protons and neutrons, as being the same force as between quarks. But they have the same origin fundamentally, but they're actually very different manifestations. In fact, the force between quarks is hella strong compared to the force between nucleons. And the best explanation I can give you right now, we will eventually draw the Feynman diagrams that will help this make sense, but the best explanation I can give you right now is the following. If I take a electrically neutral atom, okay, there's a very strong bond between, say, the electron and the proton. And then I can take another electrically neutral atom. There's a very strong bond, okay? However, if these are in some dipole configuration, if they have some angular momentum where this has some net dipole, and I bring these two electrically neutral atoms together, they can interact with each other through their dipoles. All of that is electromagnetic interactions. But this van der Waals interaction between two dipoles is much weaker than the actual interaction binding the electron to the proton in each of them. That's exactly how it plays out for quarks versus nucleons. So the nuclear force between nucleons is much like the van der Waals equivalent of the strong interaction between quarks. And again, we're going to see some diagrams which will help convey that. And you'll see in the diagrams why it's so much weaker.
Is there a property that governs what kind of particles interact via the weak interaction? So you have E and M and charged particles have those interactions.
Yeah, if it exists, it interacts with the weak interactions. And I'm not kidding you, like everything interacts via the weak interactions. There is nothing that is untouched by the weak interactions. If it exists, it feels the weak interactions. The only thing that might exist that doesn't is a sterile neutrino. And this is a part of a backstory. If you want to try and give neutrinos mass, then they have to have a right-handed component because you only have left-handed components. Neutrinos are massless. But if they have mass, then you have to allow right-handed components, but those right-handed components can't participate in the weak interactions because the weak interactions are SU2 left. So you've strangely got these neutrinos out there, and they don't feel the weak interactions. They don't have charge, so they don't feel the electromagnetic interactions, and they sure as hell ain't quarks, so they literally don't interact, and they're called sterile. And the only thing they can do is have mass, which will affect general relativity and gravity, but they don't interact with any of the standard model forces. So that's the only exception to that.
If you have a particle that can't interact with anything, how would it ever be created? Or
Well, this is this idea that you can. That is an interesting question, but you have to remember that is the right-handed. Yeah, I can't get into it. It's way more complicated than I don't even think I could say something truly intelligible about it right now.
Okay.
I would have to think more about it, but I mean, it does interact gravitationally. So it is playing around with the universe, and certainly early in the universe, there are possibilities of gravity providing, the creation and annihilation of particles, much like the other standard model forces. Right now, gravity doesn't really do anything in terms of decay, like the other forces, but early in the universe, who knows? And these sterile neutrinos, you guys have heard of dark matter, this stuff that's out there that doesn't interact with anything, but it has mass. Well, these sterile neutrinos are a possible candidate for that. Of course, it's really hard to design experiments to detect them because they don't interact.
Is that something that we claim actually exists, though, the sterile neutrinos?
Well, and I'm not an expert in neutrino mass, in the physics of massive neutrinos. If you got Griffith's book, he discusses this towards the end. But I wouldn't say there's any definitive answer. There's certainly no experimental proof. It's a nice story that if the neutrinos have mass, then you need to have these sterile neutrinos, and we've got this problem of dark matter, so maybe one problem solves the other. But there's also other candidates for solving the dark matter problem, but I'm not an expert in that.
You said the weak force interacts with everything. So how do photons and gluons interact?
How do you? They don't.
Is that like a nonsensical question to ask?
Well, actually, yeah, photons and gluons do not interact.
And they don't interact with
When I say the weak interactions interact with everything, the weak interactions interact with all matter particles. The weak interactions interact with photons because there's underlying this an electroweak symmetry, but they do not interact with the gluons. The gluons are the one thing that the weak interactions can't touch because they're completely different symmetries. But gluons aren't matter. Other questions? So a lot of the questions you're asking, it's interesting because you're going to get a better appreciation for the answers to these as we move through doing calculations and understanding these Feynman diagrams. So it's nice that you're curious about these things, and we'll see how far we can get in covering some of this. So what I'm going to do today, I thought about going straight into interactions, not interactions, but calculations today. But I kind of realized that since we've been on this sort of journey through symmetry and the importance of symmetry in the standard model, that we might as well just take this moment to finish the story of symmetry, and then we can take it and we can proceed to look at some calculations. And what I have in mind here is all of our discussion of symmetry so far. We've talked about Lorentz transformations and special relativity. We talked about rotations and non-relativistic physics. Those Lorentz transformations and rotations led us to the ideas of tensors and vectors and dual vectors and scalars and spinors, as much as you hate them. So we talked about those transformations and theories which have those symmetries. And then we talked about SU2 left cross U1 hypercharge, SU3, those transformations, which if you gauge them, make them local, then they give rise to interactions. All of those were continuous. So back in our first introduction to groups and sets of transformations, we said there's these continuous ones. There's an infinite number of group elements, but they're continuously connected. So I can rotate by any angle I want to in a plane. I'm not restricted to 90-degree rotations. I can rotate by upsilon if I want. Now it's time to go back and say, okay, wait, are there any discrete groups that we should think about? And it turns out that there are. Okay? There are three very, very important discrete groups that are relevant for standard model physics. And what's actually interesting is that contrary to, say, rotational or Lorentz invariance, which we assumed was a part of the fundamental symmetry of the standard model and has always been borne out by experiment, this story played out differently. Initially, everyone assumed that these were symmetries of the standard model, so much that they didn't even bother to check with experiment. And then eventually people started going, well, maybe we should check that. And when they did, they found out, holy crap, these things are not symmetries of the standard model. Okay? And there's some really interesting consequences, some really, really interesting consequences of this. We certainly won't go through the entire discussion today, and a certain very important piece of it will probably have to be delayed until we get a little bit of Feynman diagram drawing under our belt, because I can't really explain CP violation without drawing some Feynman diagram stuff. So, but for now, let's just kind of start talking about these three transformations and where they are and how they arise in particle physics. And I'm actually, everybody says CPT, but I'm going to do it this way, PCT. This is the order in which I'll talk about them. But the P is parity, C is charge conjugation, and T is time reversal. Now I know what you're probably thinking to yourself, wait a minute, Alex, time reversal. Time reversal is not a symmetry. Oh, you can't go backwards in time, that's bullshit. And this is a very, very interesting, very, very deep idea in physics that, truthfully people still wrestle with. And that is, macroscopically, you certainly don't see things happen if you reverse the direction of time, right? We grow old, and if you reverse time, we all grow young, and nowhere in the universe are people growing younger. Like, it doesn't happen. All right? So there's something about the forward march of time. You cannot see the same thing if you go backwards, okay? However, if you are willing to ignore big stuff and go down to the microscopic scale and say, take a proton and send in an electron, actually that's not the way it would scatter, it would scatter like this, okay? If you made a movie of that, and then you reverse the movie, you would see an electron start here and come in and scatter off a proton. Both of those are perfectly legitimate events with the electromagnetic interaction that you would use to describe this. So microscopically, systems exhibit time reversal invariance, or we think they do. They actually don't, but we think they do, even though macroscopically they definitely don't. Of course, there's a huge, very deep story connecting microscopic to macroscopic physics. And for those of you who haven't, when you take thermal physics, that's where you'll learn that connection. And that's a very interesting set of ideas. And I hope whoever teaches you that course can get you enamored of it. But anyway, so that's what we mean by time reversal invariance. But let me start by talking about parity. So, first of all, well, before I get into parity, just to connect to some of the things we talked about when we were talking about groups in general, these are all discrete groups. That means that if I gave myself enough time, I could actually list the group elements. In fact, I can list the group elements because these are really, really small discrete groups. In fact, they're the smallest discrete group you could possibly imagine. Each of these is an example of a group which is often called Z2. Z2 is the simplest non-trivial group you can imagine. What's the simplest trivial group you can imagine? The identity. It's got to be the identity because every group has to have the identity. And so if the only thing you have is the identity, that's the most trivial group. This is the second most trivial group, and it is a group with two elements. One of them is the identity, and the other one you can just call G, but you can immediately determine everything you want to know about this group. For example, you can immediately determine that G times G has to be the identity. Therefore, G is its own inverse. You can immediately conclude that it is an abelian group. You can multiply the two elements in any order and they automatically commute. The identity commutes with anything. Okay, and it exhibits associativity, all this other stuff. So this is a really simple group. There are many, many different representations of this group. And this is where I floundered before, but we can think of even and odd as a representation. And we can think about multiplication by plus and minus 1 as a representation. Okay, lots of different ways of representing this. In fact, P, C, and T are three representations of this group. Physically, they mean different things, but their group structure is the same. They're all Z2. They're a two-element group. They all have the identity and then one non-trivial thing you can do. Okay? So that's the sort of, yeah.
When we say charge conjugation, that's talking about electromagnetic charge, not...
Let's not jump ahead. I'm going to come to it and talk about it. So, no, not exactly. Something deeper than that. And we might or might not get to charge. Well, we won't get to charge conjugation today, but perhaps next time. So let me start with parity. And so you might remember when we talked about rotations and spatial rotations, we said we wanted to work with SO3 instead of O3. So this has the determinant of a rotation equal to +1. Here, the determinant could be plus or minus 1. So in going from O3 to SO3, we get rid of those transformations which have a determinant which is -1. And the transformations that we threw out in going from O3 to SO3 were actually parity transformations. Because if I think about a parity transformation, one way to think about parity, which is what most people like to think of, is a mirror transformation. So, I got some person, and they're standing there flashing you a peace sign, like Claire in her picture for this class. And if I reflect them in a mirror, that's what they would look like, okay? So reflection in a mirror is reflection along the axis perpendicular to the mirror. So if I call this the x-axis, reflection along the x-axis turns that person into that person. And you'll notice, pay attention, this is discrete. I cannot take this picture and rotate it into that picture. Right? If I take it and do this, he's facing the other way. Okay, if I take it and flip it over this way, he's now upside down. You cannot take this and rotate it into that. Okay, so this is a discrete transformation. In terms of a coordinate transformation, we could just represent this by -1, 1, 1. It changes the sign of the x coordinate of whatever it's acting on. But what's the determinant of that? It's -1. Okay? So these discrete transformations, these parity transformations, are exactly what we threw out to say, to get down to SO3 is the set of rotations. And we needed that because we know that rotations are continuous. They form a Lie group. They have all these nice properties. Okay? But now today we want to go back and we're going to start talking about the discrete ones. Now, this is not a good way to think about parity because it's not democratic. It treats the x-axis as special. And last time I checked, there was no special x-axis out there. So our definition of a parity transformation will actually be reflection on all the coordinates. So if you reflect on all the coordinates, what happens to this picture is that you actually get that. Okay? Which, stare at it for a minute, and you'll see again that you cannot rotate this into that. Yes?
Doesn't that not work if you have an even number of coordinates?
Yeah, exactly. So we have to reflect an odd number, and exactly what you said. If I use that as a transformation, that's got determinant +1, but that's actually a rotation.
Right.
This is actually a rotation by 180 degrees around that axis. So it's only if you flip an odd number of coordinates that you're genuinely doing something that's not a rotation.
So is that, I guess it doesn't apply to space-time.
Yeah, no. So all of this can be extended to space-time, and that unfortunately is where we'll eventually get to the time part of this story. But for now, and that's going to be a very, very interesting observation, which we'll come back to at the very end. For now, though, we're only talking about space. So we're reflecting X, Y, and Z. Hands across America. Look at that. You got hands up everywhere.
I thought at one point we had said that the parity transformations couldn't form their own group because it's not a closed group if you have the determinant of 1 equal to negative, so the determinant of two things multiplied splits into the determinant of 1 times the determinant of the other. And if they're both -1, then the...
Okay, yeah, that's okay. So what I said, and I'm glad you asked that, it's a technicality, and if you go back to the lecture notes from when I said that, you'll see this discussion. What I said was, I cannot take the transformations with determinant equal to -1 as a group. I can't take the stuff I throw out and by itself form a group. And the reason I can't do it, if for no other reason, is I do not have the identity. But you'll notice parity is the identity and G. The identity has determinant +1. And then G has determinant -1. So that statement I was making about you can't just take the stuff you're throwing out and let that form a group is true. A, it's missing the identity, but B, if I take two of these with determinant -1 and I combine them, I get something with determinant +1, which is no longer part of that set. But that's not the case here because this set of transformations includes transformations with determinant +1, the identity. So that might have come at you a little bit quick, but again, I talked about it in a little bit more detail in those notes from the lecture where we did that. Yeah.
So can we call the identity a parity transformation? Because you can rotate and do the same function.
Sure, it is an element of the parity group. It's just not one that we're going to find particularly interesting. It's
Right.
like the identity is an element of the rotation group, but it doesn't really tell us anything useful.
But I thought we considered a parity transformation can't be obtained by strictly rotations, whereas the identity could be.
Okay, I'm sorry. All right. So let me back up. I'm okay. A parity transformation, when I say that word, is this element here.
Okay.
It is part of a group.
To complete the group we're throwing.
Yes, which you have to include the identity with to actually form a group. But when I say P, I'm referring to this element. So I'm not saying that P is the set of these. I'm saying that P is that one transformation that's non-trivial. That's a good point. Okay, I'm going to boldly venture on. Okay, so we can ask ourselves, is parity, so we've established that rotations are an invariance of physics. Okay, microscopically, macroscopically, we have spontaneously broken rotational invariance, but does microscopic physics have parity invariance? That's a separate question. You can't conclude it from rotational invariance, right? Because parity is not a rotation. Okay, so let me reiterate that. If you ask yourself, is physics invariant under a rotation by 90 degrees? The answer is yes, because physics is rotationally invariant. And a rotation by 90 degrees is a rotation. Okay? I cannot say that physics is invariant under parity because it's rotationally invariant, because parity is not a rotation. I have to check it separately. And this is interesting because until the 60s, no one thought that parity would not be a symmetry of nature. And then finally in the 60s, someone said, "Hey, should check that." And they did, and it wasn't. Bam! Okay? Now, bear in mind, the 60s is actually before we really understood the weak interactions. So we have been writing down theories which break parity. SU2 left. It treats a left-handed thing different than a right-handed. That breaks parity. But I'm giving you what we know now. Okay, but that's not until the 70s that the electroweak unification was really written down and understood. So we're going to go back in time a little bit. So is parity a symmetry of the standard model? That's a question to be posed, and then there's two ways that we can answer it. And I'm gonna go through this because it's a way that we'll kind of try and address all of these symmetries at different levels. So there are two ways to ask: is parity a good symmetry of the standard model? How would we check it? For the first, you can consider all standard model processes and their parity transformed versions. And I'll tell you what this, I'll give you an example of this in a minute. But I can just take a particular process, like this particle decays into that particle and you know, whatever. And then I can say, what would that process look like if I did a parity transformation? That's the parity transformed version of the process. If parity was a symmetry of the standard model, both of those processes should happen. There's no reason why one should happen and the other not. Okay? We good with that? And we'll see an explicit example of what this approach means. There's a second way to approach it, and that is to say we can assign a parity value to quantities, or to, we'll say to particles, but we got to be a little bit careful because you can actually have a parity associated with the configuration, the angular momentum configuration of a bound state. But we can assign a parity value to particles and then see if it is conserved. So if I take a process and maybe it starts out with a parity which is +1, and then at the end of the process the parity has suddenly become -1, parity wasn't conserved. Now, those of you who have ever heard of Nether's theorem might smell sort of a connection to Nether's theorem. Nether's theorem says if I have a symmetry of a physical theory, then there is an associated conserved quantity. So here we're tempted to say if parity is a symmetry of the standard model, then parity is conserved in processes. But we have to be a little bit careful. You can't actually apply Nether's theorem in this case, because Nether's theorem only applies to continuous symmetries, and this is discrete. But that's fine. We're not relying on Nether's theorem. We're just saying if either of these happen, then parity is not a good symmetry of the standard model. Okay, so what would a process look like that violates parity? And I'm going to have just enough time to draw this one thing, but I want to do this because this is one place, if at all, where we can connect to experiment. So consider your best friend, Cobalt-60. I know. As a string theorist, when did I ever think I would write cobalt on the board? Okay, so if cobalt-60 decays, then what we've essentially got is cobalt-60 decaying to nickel-60 plus an electron plus an anti-electron neutrino. So for those of you in the audience who have any familiarity with nuclear physics, what is happening here? Yeah, so what turned into what? Yeah, a neutron in this cobalt turned into a proton of the nickel and then emitted an electron and an anti-electron neutrino. That's exactly that weak interaction I drew on the board earlier. Wasn't that convenient? Okay. So why this particular thing? Like, why the hell cobalt? Okay. Why not? No. There's actually a reason. Okay. And this is actually the test that was done to first observe parity violation. So what we can do is the nuclear spin of the cobalt nucleus creates a preferred direction in space. There's two R's in there. Yeah. Now, why is it important to have a preferred direction? Well, if we start off with something which is itself completely rotationally invariant, then doing something to coordinates, flipping coordinates is not really meaningful. We need to start with something which has a preferred direction, and then we can talk about reflecting that direction. Okay? Now, I should actually venture back to what I was saying earlier when I was drawing the pictures of the guy, or Claire, and then Claire, okay? Even though technically parity is -1, -1, -1, when I talk about examples, I'm almost always going to just reflect one direction. That's just as good, okay? All right? Because sometimes that's all I have at my disposal. So in this example, I'm just going to reflect one direction, but just bear in mind, you can carry this whole discussion through to reversing all three. So what does this picture give us? So if I draw my cobalt nucleus, it looks like that. And because it's spinning and it's comprised of charged stuff, I have some nuclear dipole moment, so it's kind of like a little magnet. It's got a north and a south pole, and there's an axis associated with that. Okay, so this bad boy is spinning, maybe in this direction, because it's comprised of charged stuff and it's spinning around in a circle. You create a nice little dipole moment given by the right-hand rule. There goes your north pole. Hooray! Okay. And now, here is the amazing thing that was observed by Li and Yang in, I think, 1962. Or no, sorry, it was observed by Wu. This I think she was a high-energy experimentalist at the University of Chicago, but this experiment was suggested by Li and Yang. They said, look at the decay of a bunch of cobalt nuclei and measure the direction of the electron that comes out with respect to the axis of the nuclear spin. Pay attention to that. Now, why don't you measure the direction of the neutrino with respect to the spin? Because that's hard. It's hard to detect. But you can detect electrons. They're really easy. Okay? And here's what they found. What they found is that when this thing decays, the electron always emerges along the south pole. And you might say, so? Maybe that's just the way it goes. Maybe it's like wants to live in the southern equator. I like Australia. Okay? But here's the problem with this. Let's take this. So the experimental observation was that the electron always comes out the south pole. But now what I want to do is I want to p-transform this. Okay? So there's a way to p-transform, and I'm actually going to do this, I'm actually going to do this for real. That's pretty cool. Okay, so there's my little electron now. The first thing I'm going to do is I'm going to do a parity transformation in the x direction. So I'm going to flip the x-axis, where the x-axis is, oh boy, where's my x-axis? You know what Uncle Alex didn't do in his notes? He didn't draw a coordinate system. If I was in physics 1, man, I would be, oh, have my ass handed to me. Okay, yeah, I know.
I mean, the picture will be the same no matter what axis.
Yeah. So I'm just gonna pick this to be the x-axis. That's fine. No, that's not the x. Hold on, guys.
Draw some pictures.
I feel terrible about my picture not being complete.
No, it's okay.
It's not okay! Oh!
We did say we'd leave unhappy today, so.
Yeah. Okay, I'll just say it this way. And I won't worry about my coordinates. It really doesn't matter. Okay, here's the important thing. I'm just going to call this P. Nuclear spin, okay, is coming from an angular momentum, right? So there's something which is rotating. So we have something like that, okay? And that's what determines the direction of the North Pole and the South Pole. It comes from a rotation. And here's the important observation, okay? If I reflect all of the coordinates, this becomes minus r. It's whatever its original value was, negative. This becomes minus p. It's a momentum. If you reflect all the coordinates, it reverses all the components of the momentum. What do I get at the end of that? I get exactly what I started with. So angular momentum is an example of something we call a pseudo-vector. Sorry, I was trying to avoid putting in this language, but I'm just going to go ahead and do it. That is, it does not behave as a normal vector under a parity transformation. A normal vector, like a position vector, reflects, it gets a minus. Momentum gets a minus. But angular momentum is a pseudo-vector. It does not change. So if I take this picture and I parity transform it, that part of the story is the same. However, the momentum of the electron is reversed.
Wouldn't that rotation direction change?
No. I know. So this is where I think if I had drawn my coordinates in this picture, you would be more comfortable with this. But so we'll come back and we'll talk more about this in the next lecture, because we have plenty of time to talk about this. But the importance of this, okay, is that the parity transformed version of this never happens. The electron never comes out along the North Pole. It always is observed to come out along the South Pole. So according to this first test, parity, at least in this example, is definitely not a symmetry. Now this is actually directly related to the fact that there are only left-handed neutrinos and there do not exist right-handed neutrinos. It's not obvious from this picture why that's the case, but remember, creating antineutrinos actually is a very important part of the story. Okay? So I'm going to leave it there, and we're going to come back and draw lots more pictures. Were there any left over? Yes, there were. Where is?
No, that's yours. I know.
Alexander Briggs, are you here? Brandon? Jordan? Who the hell are those people?
So like, I mean, if you reflected it how we were thinking, just the spin direction would change, but then the poles would change.
Yes. Yeah, so if you reflect this across, so the problem I was having was my x-axis was actually to the right. So if you reflect it across X, the spin reverses.
But then the
This
fold
stays the
reverses.
same, but then you do a rotation in X, Y. And that gets all the coordinates reversed. And then you end up with this. So I'll draw it next time. I was having a brain fart. Because I wanted to make that the X-axis, and that's not the right axis to choose if you're going to do this, though.